Introduction. Welcome to this review of artificial intelligence and machine learning for edge computing. In the next minute you will hear a brief overall summary, followed by a section-by-section breakdown of the key ideas. Overall summary. 35. For W is merely Newton's algorithm for the output weights. 9. The CG algorithm can be summarized in algorithm 2. 6 typical training algorithms for training in MLP. Machine learning methods/algorithms are categorized in two main parts. 1.1. Supervised learning. Supervised machine learning is the most famous and most common type of machine learning. Supervised machine learning refers to the art of learning with example. 3. Learning algorithms. Machine learning algorithms are the main brains behind learning magic and making predictions. Chapter 1. Overview and background. Chapter 2. Supervised learning, from theory to applications. 2. What are regression and classification problems? Chapter 2. Core ideas. Supervised learning is a common form of machine learning training paradigm that has been used successfully in real-world machine learning applications. Although supervised learning is covered in almost all machine learning textbooks, we will introduce and explain supervised learning from an application point of view and its relationship to edge computing. Linear regression, logistic regression, steepest descent, conjugate gradient, multilayer perceptron, second-order algorithms, KL divergence, generalized linear models, kernel machines. Bootstrapping. This chapter discusses various supervised learning paradigm that is used to train and deploy machine learning models. With the recent advances in machine learning algorithms, combined with the increasing computational power, edge computing is another area of application where machine learning will be improving the current technology. We start with generalized linear models along with optimization algorithms, gradient descent, Newton's method, and metrics, mean square error, MSE, cross-entropy, used in training the model. In addition, supervised learning algorithms that capture the variation of input data distribution and algorithms that project data in higher subspace and first and second-order learning paradigms are the subject matter of this chapter. Supervised learning is a common way of training machine learning algorithms that can be later used in the inference stage on IoT and other edge devices. Section 2 covers the basic perceptron model that helps understand the learning algorithm. In Section 3, the linear regression algorithm is discussed that extends the idea of perceptron algorithm to solve supervised regression tasks. We discuss commonly used gradient-based learning algorithms along with their pseudocodes. 2. A linear regression is a weight matrix W that transforms an input vector X into a discriminate vector Y. 4. The weight W, M, N, connects the nth input to the mth output. The pattern number P varies from 1 to NV, where NV denotes the number of training patterns. For the pth training pattern, the network output vector, YP, can be written as where ZAP denotes XA for the pth pattern. To train the linear regression, we minimize the error function E that is a surrogate for a non-smooth classification error. The steepest descent gradient algorithm can be summarized in algorithm 1. The learning factor controls the step size derived in EQ. Conjugate gradient, CG, algorithm 10, performs a line search in the conjugate direction and has faster convergence than the backpropagation, BP, algorithm. Algorithm 2. Conjugate gradient algorithm. The decision boundary for logistic regression is the property of the parameters and not the training set. Since is nonlinear, sigmoid, the decision boundary can be learned as manifold learning of nonlinear surfaces. The logistic regression cost function will be as follows, EQ. Once the training is completed, the prediction for new input X is given as in order to get G, we do the following calculations by chain rule. In order to train, we minimize J, W, using gradient descent algorithm as in algorithm 3. Chapter 3, Key Concepts. Structurally, it is a linear model with softmax function, 14, at the output units. For the pth pattern, it maps the input vector xp to the output class labels as where W is a weight matrix. We review the first and second order training algorithms for MLP followed by a classifier design of MLP through regression. The input weights W, K, N connect the nth input to the kth hidden unit. Output weights WO, M, K connect the kth hidden unit S nonlinear activation op, K, to the mth output YP, M, which has a linear activation. The bypass weights WOI, M, N, connects the nth input to the mth output. The total number of weights NW equals NH, 1 plus N, plus MNH. To train an MLP, we recast the MLP learning problem as an optimization problem and use a structural risk minimization framework to design the learning algorithm. 5.18. An essential benefit of converting the training of an MLP into an optimization problem is that we can now use various optimizing algorithms to optimize the learning of an MLP. To solve for the weights connected to the output of the network, we use a technique called output weight optimization, OWO, 22-23. One-stage algorithm, in which all the weights of the network are updated simultaneously. Two-stage algorithm, in which input and output weights are trained alternately. The first-order learning algorithms update the weights of the MLP based on gradient matrices, that is, the first-order information, hence the name. We start by discussing the training of an MLP with a one-stage algorithm. In this, we train both the output and input weights simultaneously using either BP or CG algorithm. However, due to the non-convexity of error function, EQ. In each training epoch, we update all the weights of the network in a BP algorithm as follows. Here, W is a vector of network weights as W equals vec, W, WO, WOI, and G is a vector of network gradients G equals vec, G, GO, GOI. Z is the optimal learning factor that is derived using a Taylor series expansion of the MSEE, expressed in terms of Z, as 26. The BP algorithm can be summarized algorithm 4. During BP training, input weights are sensitive to input means. The input weight gradient matrix G is found as updating the weights. The GI and learning factor differs for each output. The optimal MLP will have different hidden units with different input weights for each output. We present two one-stage algorithms, namely Newton-S method and LM, and then a two-stage algorithm called as OWO multiple optimal learning factor, 2830. We calculate the Hessian and gradient, H and G of the MSE error function where the elements of H are given by we calculate the second-order direction, D, by solving the set of linear equations with OLS assuming quadratic error function in EQ, 9, and H to be positive definite, applying first-order necessary condition, FONC, 31, on all the weights in an MLP. We update the weights as the Newton-S algorithm can be summarized in algorithm 5. Chapter 4, Deeper Analysis. The LM algorithm can be summarized in algorithm 6. The error of the resulting generalized linear classifier, GLC, is where op, I, is defined as f, yp, I, and f, denotes the sigmoid activation function. A second-order feed-forward training algorithm for a radial basis function, RBF, classifier is described in refs. 9. The RBF objective function is where yp, I, is the ith element of the output discriminate vector equating the gradient of ERBF, W, to 0. We solve for the output weight matrix we using OWO, 37. In a nonlinear SVM, K, XP, XQ, XP, T, XQ, is called the kernel function and XQ, is a feature function. The coordinated descent algorithm, 39, is used for training. Decision tree, 40, is an upside-down tree-like structure generated from training data with the main root at the top as shown in Fig. Decision trees are used for both approximation and classification data. The split decision for approximation data is made based on the variance of the node. The decision for classification data is made based on information gain, Gini impurity, or chi-square. Decision trees are also more prone to changes in the data. Decision trees can be used in various applications as they can process both categorical and continuous output data. If M equals P, the random forest algorithm will work similar to bagging, algorithm 7. 1. Create n bootstrapped data, where n is the number of decision trees. 2. Build n decision trees using each of the bootstrapped data. 3. For testing, fit a new data with all the n decision trees and get the output with most votes. Out of all the data, 1/3 data are never used during training due to bootstrapping, called an out-of-bag dataset. During the start of training, the sample weights, W, are initialized as for each NV. The final discriminate for K classifiers is where components dic, X, are hardened, algorithm 8. 64. 6. Update the weights for correctly classified data by using EN equation if XP classified correctly by CK alone. 7. Update the weights for misclassified data by using plus EN EQ. These adjusted weights are used for training the next decision tree. We find the incorrectly predicted class by our model. We built a new model based on the gradient values as the predictors. The final prediction is the weighted sum average of all the predicted models, algorithm 9. The learning factor is a hyperparameter used to predict new variables is a small value, usually 0.1. Chapter 5, Conclusions and Takeaways. Machine learning methods/algorithms are categorized in two main parts. Supervised machine learning is the most famous and most common type of machine learning. Supervised learning is a technique and it is used in machine learning with the help of certain algorithms that implement supervised learning in different ways. Unsupervised machine learning algorithms try to infer a function to find hidden relations between data points. 2. What are regression and classification problems? The target variable can go as low as 50,000 to as high as 10 million. 1 and 2 gives pictorial representation of the two supervised learning problems we discussed. 2 diagrammatic representation of regression problem. Machine learning algorithms are the main brains behind learning magic and making predictions. First, we will discuss the regression algorithm. Don't confuse regression used in the context of an algorithm with that of a problem. A regression problem is a category of machine learning problems, whereas a regression algorithm can be used to solve both classification and regression by just tweaking the output generating step a little. The other algorithm we are going to talk about is a tree-based algorithm like a decision tree. A linear regression algorithm attempts to establish relationship between independent variables, x, and dependent variable, y, by fitting a linear equation to the observed data, 1. A linear regression line has an equation of the form y equals a plus bx. The aim during training is to minimize the value of cost function, which is proportional to ype, 2, where yp is the predicted value by algorithm for an observation and e is actual value of target variable for its observation for some fixed value of a and b. Logistic regression is a linear regression model with a modified equation for dependent variable used for classification problems. Decision tree is another important machine learning algorithm, variations of which are used widely by the practitioners. Decision trees can also be used for both classification and regression problems. There are numerous machine learning algorithms, each having its own advantages. Variants of decision trees such as random forest, XGB model, etc. are widely used algorithms in the field of machine learning. To measure the quality of the machine learning model, we need to validate its output using an evaluation metric. One of the most important steps in supervised machine learning is to choose an appropriate evaluation metric for the problem at hand. Just for heads up, When provided with appropriate data, any problem can be solved using supervised machine learning. Closing. That brings us to the end of our review of artificial intelligence and machine learning for edge computing. Thank you for listening. If you found this helpful and would like more book summaries like this, please subscribe to the channel and turn on notifications so you never miss a new video. Tell me in the comments which book I should review next, and I will see you in the next one.